All right, hello and welcome to CS16. My name is Lawton Nichols. I realize that you cannot see my face, but I have a solution for that. Let me open up Photo Booth. Hello, this is me from my apartment in IV. If you never come to office hours, you might never see my face again, which is an interesting concept. But I am just a grad student, so you do not have to call me doctor or professor. Please, this is my whiteboard. Please just call me Lawton. Or Lawton, if you like to pronounce your T's. So yeah, welcome. This is our first lecture. I'm going to go through a lot of things. It might take a bit longer than a normal classroom lecture, but I hope you understand and that you're doing well yourselves. All right, so in this class, we're going to learn the programming language C++ that you may or may not have heard of yet. Really, we're learning the C part of C++, and the whole reason that we want to learn this language is because it's nice and it's low level. We get to interact with the machine a lot more than we would in a higher level language like Python that I assume that most of you are familiar with. And yeah, a lot of big companies like to use C++. Google, for example, writes a lot of code in C++. So if you're looking to get a job as a programmer, C++ is a great language to know. And yes, we're going to learn about what happens when your programs are actually run. So we want to talk about exactly what things are looking like in terms of memory and just the low-level features of your code, how it's all executing under the hood. We're going to learn how to debug. So we're going to be writing a lot bigger programs than what you're used to, and that's the point. We need to learn how to do more complicated things because that eventually lets us get to solving more exciting problems. And I hope that the labs in this class will be a bit more enjoyable because they're more involved and they feel like a real accomplishment once you've completed them. So, all right, here I've had to change these around. We used to use iClickers because I like to ask you guys questions in classes. So you'll see those in all of my lectures. I'll be asking some questions for you to pause and think about, but I guess you can just pause your video and think about those instead. I will be assigning stuff, reading in the homeworks from this textbook, and you should definitely not go and search for that title on Google because one of the first links will be an illegal copy, and we don't want you to download that one. Definitely not. All right, so I think I'm going to get away from these slides now and go to the course website and talk about that and everything. There's a lot of accounts you have to make, so let's get started there. So our course website is UCSB, let me zoom in, UCSB-cs16.github.io/S20 for spring 20. Spring 2020. And here we are. All right, so there's a lot of stuff going on. I think this information tab is going to be very helpful. We'll go through all of these in just a second. But the first thing, and the thing I think you're most interested in, is the syllabus. So we click there. And the thing that you're most interested in the syllabus is the grading portion. So I used to use iClickers in every other version of this class, but now there's not really any way for us to interact. So if I can't figure out a way to have any kind of participation, I might just get rid of this 2% and put it into the homeworks and quizzes. Those become 15% instead of 2%. And then labs are worth 35%. We're going to have 2 virtual midterms, open book, open notes, I think, and a final. So that is the plan. I'll go through those in a second. And let's see here. These are how grades are assigned. There's no real curve or anything. I'll increase your grade by some amount. You're never going to get a worse grade than what you've earned. So there's that. And yes, please find a way to get this textbook because some of your homework problems are going to be based on those. And I think you can read the rest of this yourself. Yeah, so I've talked about grading and I've talked about the breakdown of things. So yes, instead of doing homeworks, you're actually going to complete a quiz on Gaucho space, and I'll give some examples of that in a second. But let's go back to the homepage because these 4 links up top are going to be very important. So let's just go in order. So Piazza is something that I want you to sign up for. It is going to be where we ask questions and receive answers. Right now you'll only see this one. The rest are like only visible to us instructors. So here is Piazza. What you can do is you can ask a question or post a note, and you can ask that question anonymously if you'd like to as well. And I'll add some more folders here, but you can say, oh, this question is about homework 1. It's about a lab, and I'll add these in just a minute. And yeah, so that's Piazza. Please go here, and I'll be using this to post any announcements as well as answer all of your questions. So try to use Piazza instead of emailing me or the other TAs and tutors in this class. That's one place where we all get notified if you ask something. So yeah, use Piazza and check Piazza. Keep your emails, keep your email notifications turned on for sure. And okay, the next thing is the office hours. So this is the same link. This one right here is the same link as this right here, the labs and office hours links and calendar. So our class normally meets at these times, but obviously we have some things going on. Instead of labs, or instead of coming to class, you all know that you're watching this video. So classes, lectures are pre-recorded. Office hours and labs are all on Zoom. Okay, so this is going to be interesting for both of us, I know. These are all of the staff associated with this class. I'm Lawton, Sherry, Yukin, Harlan are our TAs, and everybody else is a tutor who is an undergrad just like you. And we're all here to help you. The TAs, though, will be leading the labs, and the tutors will be there as well to help you individually. So here is the idea as far as labs go. For your lab, you will connect to the TA's Zoom link to attend. Attendance is not mandatory or anything like that, but if you want to attend lab and you need to get help on anything, you want to ask any questions, you want to listen to the TAs give their presentations, you will go down here, look at the labs, and then find your time. Let's say I'm in the 4 p.m. lab, and you look at the TA who's on duty for that particular time. So Sherry, let's say, is leading the 4 p.m. lab. Please recheck this. This might change. So Sherry's our TA, and so then I will click on this Zoom link to join Sherry's lab, okay? Because she'll be leading that. That is the idea. So for each lab, make sure to keep checking because the TA leading your lab might change across weeks, so please check before each lab on this page. And then for office hours, you will also use Zoom to connect to one of our, to talk to one of us on duty. So this is all going to change. This is all, I'm recording this before the class starts, a week before, so that's why things might look a little bit different if you come to this page in about a week or so. But the idea is I'm going to have office hours from these times, and you can see who's going to be having office hours for a certain time on a certain day, come up and click their Zoom link and talk to them, okay? For example, maybe on Wednesdays, we have from 11 to 12. If you want to ask somebody some questions from that, during that time range, you can either talk to Justin or Jackie, and you'll click on their corresponding Zoom link. That's the idea, okay? So we'll learn together. This is all going to be weird, I know, but hopefully that makes sense. And we might update the whole policy on this if we find a better way to do things. So that's what I got for you there. That's how labs work. That's how office hours works. We've gone over the syllabus. We've gone over Piazza. Okay, let's talk about some other things. So for labs, when you go to lab, you're going to be completing some kind of task, and you're going to be turning that in for a grade. So lab 00 is the one that you're going to do first, And instead of clicking on these and looking at it this way, you can see the assigned date, and you can see the due date of all these things. Same for homework, same for exams. But something that you should be looking at instead is this course calendar. This is a very interesting and useful page to go to because it takes all of that and it puts it up here in a nice format that you can actually maybe understand a bit easier. So on Monday, we're assigning homework 1 and lab 0, and lecture 1 is happening as well. So you can click on all of those pages. These are all links to different things. But for lab 0, for example, you can see when it's due. It's due on this Sunday, the 5th. Okay? So when you go to lab 0, you'll have to do a bunch of things. You'll follow along. But when you submit, you're going to submit to this gradescope.com website. And that is this right here. I should be giving you an invitation to this. You should have seen that in my Gaucho Space invitation welcome message thing. Hopefully you've been invited to this. If you have not, please ask us on Piazza to add you. But here you can go to say, I want to submit for lab 0. And then I'll say something like, oh gosh, there's submissions. You'll see something like upload submission, and then you can drag your files into here because we haven't learned how to use Git yet. And that's how you'll submit your lab. You'll click upload, okay? It'll look a bit different for you since I'm the instructor. Okay, so that's how your labs are going to work. You're going to go to this Gradescope website to actually upload them and get a grade for them. Most of them are auto-graded. Some of them have some manual grading along with them as well. Okay, so that's labs. And if I go also to, maybe I can go to homework, or maybe I can go to the same homework from the course calendar. Your homework 1 is assigned and due also on that Sunday, okay? This should be a very simple one, this first one. But homeworks involve you reading parts of the book and then completing some questions, but you don't have to turn in homeworks, okay? Dun dun dun. You don't, no, I didn't mean to go all caps. You don't have to turn in homeworks. Instead, you will complete a quiz about them on Gaucho Space. Okay, so that's what homeworks are. So you're going to do all of this so that you can do well in the exams, but to actually turn in your homework, that is, you'll be just completing a quiz on Gaucho Space. So here is our, there it is. Here's our Gaucho Space page, and here you can click on homework 1 quiz and then go and complete that, okay? That's the idea. You get 1 attempt, so do well. And yeah, that's the idea. So homeworks will be quizzes, not actual physical things that are turned in. All right? And then, I guess the last graded portion of this class are the exams, which they're all grayed out right now because I haven't finalized all the details. But your first midterm, you're going to have 2. Your first midterm is going to be week 4, before the drop deadline, which is nice. Week 4 is your first midterm, that Wednesday. Then week 7, May 13th, will be your second midterm. And then your final is on the Thursday of finals week, it looks like. Yeah, Thursday. And it'll be from 12 p.m. to 3 p.m. So I hope that is all making sense. I still have to decide exactly how midterms are going to happen. I'm thinking about making them be like online things on Gradescope, but I'm heavily leaning, even if I do that, I'm heavily leaning towards open book, open notes, open everything. I can't, like, I don't want to use that ProctorU thing that everybody hates. Okay? So that's the idea for all of that, and because I'm just talking to myself right now, I can't anticipate your questions, so please ask me things on Piazza, yell at me somehow if you have any concerns or I say something wrong and you want to know more information about anything like that. Please find a way to get in touch with me or the tutors or the TAs. We're all here for you. All right, so that is a lot of the logistics. I think I've gone over everything. I think we can go back to the actual slides now. Oh, the one thing I haven't gone over is this lecture notes thing. From this, I'll post our lecture notes in a few different ways. We have our slides that you can look at. That's all the stuff from today. for each lecture. And then here on the lecture page, what I'm going to do is I'm going to post the lecture video. And for this particular lecture, I'm also going to post some videos about how to get a terminal on your computer, and that's very important so that you can have that before your lab. So please watch those as well, at least for this lecture. So normally there's just going to be one lecture video posted here to each lecture page, and that's where you're going to go to see that lecture in time for it. It'll always be posted sometime before the actual lecture time. Okay, so you go there and watch your video, hopefully ahead of time, so you can come to my office hours. Okay, and I think with that, that is everything here. We've talked about this link. Everything that I've been writing over here is called my whiteboard, and I can also draw with my tablet. So you're going to get all of these notes, and it syncs. So if you just click this link and find the appropriate day, the name, the lecture thing, by clicking this, you should have access to everything I write in class any day. So that's super useful. And then every time I write pieces of code, I will also post that to a different place. It's going to be a website called GitHub. And that is the final piece of the puzzle. And that does remind me, GitHub, this is going to be a website where you upload your actual lab submissions. You will upload your lab submissions to GitHub as well as Gaucho Space. And this will happen eventually. I don't think it happens for the first lab, but eventually it will. You'll be doing this, so make sure to get a GitHub account and sign up for our GitHub organization, because that allows you to make these virtual folders called repositories, so that we can all, as instructors and staff, see your code and give you any feedback on it, or do things for manual grading, for example. And also in this repository, this is where I'm putting the starter code for all the labs, as well as all the code that I write in class. So when you click on this actual link right here, it'll take you to this actual repository that will be filled in with different folders for every day that we have a lecture, and I'll put the code there. Okay, so I hope that makes sense. And now finally, I think we can go back to the slides for today. Here we go. Normally I'd ask you to take your iClickers out, but I'm going to just have to extrapolate from my previous classes what you're going to answer here. So I don't assume that you're familiar with C++. I assume that you're familiar with one programming language, because CS8 is a requirement for this class. So if you're coming from UCSB, you should have learned something like Python. If you're coming from maybe a community college, maybe you've learned something like Java or C, or maybe even C++, who knows. But I assume that you have some programming experience. If you don't, this might not be the class for you. Okay? And then also, I don't expect you to know much about the command line, the Unix command line, the Linux command line, or the terminal. We're going to teach you all of that in this class. But if you do have any experience, or you want to start getting more experience by searching online, this is a good thing. All right? So let's talk about a computer. We'll start very general. There's 5 things that your book talks about. Let's just make sure we're all on the same page. I'm going to actually copy this into our notes for today, because why not? So we have these 5 different things that we like to talk about that make up a computer, and they all do different things, right? So let me try and put these in different places so I can write notes about them all. Main memory, and then secondary memory, let's say it goes right here. So normally I'd ask you to give examples of these, but I'm talking to myself right now, so I'm going to have to do it myself. I wish I could put the notes in a different spot, because I think when I type here, it'll go. Oh, good, cool. All right, so an input device is something like a keyboard, or a mouse, or even a touch screen. They're all things that allow you to give input to the computer in some way, some kind of physical thing gets translated into digital electricity waves, something like that, and then on your computer I press this key, I see a space. Okay, so that's input. You can give things to the computer for it to work with. You can give information to your machine in some way. And then output's the exact opposite. It's taking stuff out of the computer. So you have your screen, maybe any flashing lights, anything like that, like my charger cable is blinking green because my computer is currently charged. Anything like that is just a way for the computer to give you back information in some way. And then a processor is the thing that's actually going to run your code, so aka CPU, this runs your code, we say. So it's actually doing the thinking, right? It does the thinking. So when your program is being run, it's being fed into your computer's processor. And in terms of like writing a program and executing a program, let me give an example of all these things. So when you're writing a program, you're going to use your keyboard to type the text of your program. And then an output device will use the screen to print out the results of your program. And so, of course, the processor is actually going to run your program. The main memory is something you may have heard of as RAM. That's one example of main memory, which stands for random access memory. And that is it's a place in your computer's memory where your program gets loaded here before it's run. So we take this program, we put it into main memory, and every time your program wants to execute another line of code, the processor gets it out of main memory. And take that last sentence with like a grain of salt, because that's not exactly what's happening, but that's the idea. Your program lives in main memory when it's being run, but your processor, and then your processor is going to ask for the next instruction when it needs to be executed. And then secondary memory, some examples of that are like a hard drive, flash drive. It's things that are farther away from the computer that can't be accessed as quickly, let's say. Hard drive or flash drive. Those are probably the best examples that I can think of right now. So these are slower to read from, but can hold a lot of stuff. So for example, maybe you have a hard drive with 500 gigabytes, but your main memory you only have maybe 8 gigabytes of RAM. It's harder to come by. Main memory is a lot faster to read from. It's very fast to read things out of main memory. And so that's the idea. So you store your program gets stored on your hard drive, or maybe your solid state hard drive or whatever, and then when you want to actually run it, it's going to be transferred to the main memory. Okay, so you're kind of taking stuff from here, giving it here, which is then going to take it, start executing it there on the processor, and then finally we output on the screen. And then the initial thing is, hey, we save our program on our hard drive, which is our secondary memory. So that's how these all fit together, and I hope that makes sense. Again, please yell at me on Piazza or something, or come to office hours if none of this made sense. So that's the idea. That's the bird's eye view of all these different components of hardware. And I think we can move on now. So yeah, like I was talking, you have this first stage when you're actually writing your program. You're editing it, you're talking to a text file, you're saving things. That's something you've already done. You've written, for example, Python programs in some kind of text editor. The new thing about C++ is that it's a different kind of language. It actually gets what's called compiled before it's run. So let me talk about this over here. So C++ programs get compiled before they are run. Compilation is the process of compiling. It takes your input program in a form readable to humans, like your Python program. It's very easy to read that as a human, relatively. And compilation transforms this program, into a form that is readable by a machine. We call this machine code or assembly, things like that. And one reason that we do this is machine code can be read and executed very quickly. This machine code can be read and executed very quickly. So, for example, if you write a Python program to do one thing, and you write a C++ program to do the same thing, just without anything extra, without thinking any harder about the program, it's most likely that the C++ version that got compiled is going to run about 100 times faster, if not more. Okay? That's the idea. So yeah, this kind of compilation process, it's down here as well. So a compiler is going to take this program that you've made and transform it eventually into a program that you can actually run. And running is executing that whole binary program on your computer. There's also an intermediate step called linking. So the compiler compiles your code, but that's just one of the processes. So let's say we have our file. Our program is p1.cpp, because .cpp means a C++ program. All right, and so we can give that to the compiler. And that's going to take it and output what's known as object code. Object code. You don't really have to memorize these words that I'm giving you right in here. This object code thing is not something I'll be asking you about on a quiz, but compiler and linker are very important. And eventually you can give this to what's known as the linker, which will take all your stuff and actually make a final program, a runnable program. If you want, I don't know, if you're on Windows, it's .exe, right? So this is actually a runnable program. The whole reason that we have a linker is because, say you have a program with multiple files, well, they're all going to get compiled separately. Let's say you're also going to make a program and use P2 in it as well. So again, you'll give that to the compiler, and it'll output, I don't know, P2's object code. And the idea is you can give them both the linker, and the linker will bring them together. It links things, right, into the final executable, runnable part of the program. So the compiler makes machine code while the linker puts together a bunch of different pieces of machine code so that you have one big final program to execute. For example, the print function, which is called something different in C++, but we'll get into that later. The print function is implemented in a library somewhere. It is implemented in a library outside of your actual, of any of your code, of your p1.cpp, your p2.cpp, your p1.py. So the print function it's living somewhere else. Linking brings in that implementation so that your final program can use the print function. Okay, that's the idea there. So that is the whole process of translating this program in what we call a high-level language, something that's close to English, all the way down to machine code, which is ending up being this binary representation. It's going to eventually be ones and zeros because that's how we store things in a program. Okay, so now let me give you an example of writing the world's simplest C++ program. Okay, I'm going to go to my favorite text editor. I'm going to call it I'm going to use Visual Studio Code as my favorite text editor. you can pick whatever one you want. I'm going to use this one called Visual Studio Code. And then I'm also going to open up a terminal for today as well. Did I not already do that? No, I did not. So let me go here. Let me make a new window and make it big so you can see it. Default, please. So this is the idea. You want to install a terminal on your machine. If you have a Mac, it's a bit easier of a process. But if you have Windows, I've made a video for you to go and find your own terminal. I've made a video that helps you install something called VirtualBox, which makes a virtual computer inside of your computer. So please make sure you have an editor, like Visual Studio Code, and a terminal. The one that I like to use is called iTerm2, but the one that you have already on your computer or that you install based on my videos is totally fine. Okay? So, all right, there's a lot of stuff going on. I want to write this program, but there are a lot of things I need to do first. So let's take a quick intermission and talk about this thing called the terminal, which you may have never heard of before. So the terminal is, it's another program. The terminal is a program in which you can run programs. It's all text-based, okay? So everything you output is most likely going to be text. You can start programs that make windows from the terminal, but usually you don't, okay? So you run text-based programs in the terminal, and there are a lot of different commands. Some programs are built in to your operating system and are called commands. I'm going to show you a few of them because it's very important that we learn about them. For example, the cd command means change directories. But an even simpler one first is called pwd, which means print working directory. So all commands are input and then executed by pressing enter. So you press the enter key when you want to run a command. So I'm going to run this one called pwd for print working directory. Okay? I'm going to say pwd in my terminal and hit enter. And it just so happens that I'm in this special folder that starts with a tilde called my home folder. It really stands for this on my machine, users Lawton Nichols. It might be something like home UCSBCS or users your name, something like that. That's not a problem. So the terminal is built around the concept of your current working directory. Inside of a terminal window, you're always inside a certain folder on your computer. Okay? You can change. Well, first of all, you can see which one you're in with pwd, and you can change your current folder, also known as a directory, by using the cd command for change directories. Okay? So, this is the idea. I want to get to my code from class folder that I put on my desktop inside of my CS16 folder, inside of Spring 2020, inside of S20, or inside of Spring 2020, inside of code-from-class. And that is the folder that I want. Right now it has one file called karaoke.cpp, which we'll get to in a second. Okay? I'm going to go and try and get to this folder in my current working directory. So my desktop CD, it's one away from my home folder. I can say CD desktop. I can press the tab for it to enter it in for me because it knows it's there. And now I'm in the desktop folder. If I say pwd, I'm now in my desktop. I can also move multiple folders at once by spacing them out with slashes. So I want to go inside of the CS16 folder, inside of the Spring 2020 folder, inside the code from class folder. And now I'm in, if I say pwd, I'm in this long chain of directories all separated with slashes. And I know I'm in my code from class folder. Okay, so that's the cd command. It changes directories. Okay, two special directories are ... and ... which don't make a lot of sense. ... means previous, or parent directory, and ... stands for current directory. So if you say cd dot, you don't go anywhere because dot stands for the current directory, and cd dot dot goes to the one up. So spring 2020 was the one up above from code from class, because that's the one right before it. And so dot dot will take me there. And now I can go back into the code from class folder by saying cd code from class. And now I'm back in there again. Okay, now I can get around in my terminal. What can I do there? I can see what's there by saying ls. List the contents of the directory that you're in. Current working directory. Okay, I can say ls to list what's there, and right now I only have karaoke.cpp. All right, this is good. I want to make a folder for today. So to make a new folder in the terminal, you can say make dir, like that. Make a new folder. So I can say make dir, and then the name of the folder that I want to make, and I want it to be called lecture, like 01, okay? So when I hit enter, watch what happens on this actual graphical version of this. I just made this folder called lec01. I can see it with ls, it's there, it's actually a different color for me because the terminal's cool like that. And I can change into it and start working inside of it by saying cd lec01. And I've been typing the tab for it to autocomplete for me, okay? So, right now, I'm ready to go. I know what I want. I have made this lec01 folder, and I want to make a file now inside of it, and so I'll go back to Visual Studio Code, my editor, to actually do that. And remember our end goal right now. It's writing a simple C++ program. So now I'm going to make a new file. I'll call it, I don't know, simple.cpp. This is like the simplest CPP program, or C++ program that you can make. All it does is one thing. It does absolutely nothing. Main, I'll get rid of all of this. Okay, so this is the simplest possible C++ program. And instead of hash signs for comments, this is not a comment. This is Python. No. 2 slashes make a comment. This is a comment. In C++, it doesn't actually get executed. It's only one line though. Only makes it's a single line comment. If you want a multi-line comment, one that you can just keep typing forever and have it still be a comment, you can do /* and then start typing your this is a multi-line comment. And then you can end it with */. I hope that makes sense. Those are comments. And so now I'm going to write a few comments because I want to explain what's going on here. So every C++ program starts by calling the main function. So you have to write this function called main. You have to write a main function for your program to be correct, or to actually compile and make a program that actually runs. And the fact that it's called int main means that we're now talking about things called types. Int stands for integer, just like in Python. It is the return type of the main function. Because you can see that the main function has to return some number. The main function returns a number that indicates whether the program completed successfully. This was just something that people thought of. So it's just something that you do when you're writing a C++ program. Your main function returns an integer. That's customary. That's how it works. And 0 stands for success. Oops. And any other number stands for failure. All right? That's the idea. So this is the simplest program because it's going to do absolutely nothing. This program immediately ends by returning 0 to the terminal. Because who calls the program? The terminal does, because that's where we're going to run it from. So it does absolutely nothing, but this is the simplest program. It does absolutely nothing. Okay, so that's what a C++ program looks like. And now let's see, do I want to go ahead and actually talk about compiling it? Yeah, let's do it. So let's actually compile and run this program. I'll put it way up here. So I'll make a multi-line comment. To compile this program, find it by cding to its directory. And so that way you know where it is. So get inside whatever folder that it's in. Say it's in lec01, get there, so that your current working directory is lec01, and you have this file immediately at your fingertips. Then you'll run this command, g++, the name of the file, -o simple, okay? And what this is saying is we want to run the compiler. The compiler's name is G++. It stands for the GNU C++ compiler. I don't know if it's going to say that. I don't know, help, maybe. Does it actually tell us its name? No, this is too long anyway. Whee. Not really. Yeah. So G++ stands for GNU C++ compiler, or GNU C++ compiler. Not a problem. Clear all of that. And it'll actually compile and make a runnable program for us. It compiles, or it translates our C++ program into, I can just say C++, a runnable machine code version of that code that we wrote. So after we do this, we'll have a program called simple because we use the -o. -o simple says to compile the program into a file called simple without any extension. If we didn't give that, if we didn't say -o simple, let me put this in quotes as well. If we didn't say -o simple, then the program would be called a.out because that's the default name. Now we don't like it, we want it to be called simple. So I'm going to take this, I'll copy it, and that will be our program that we're going to run. Okay, so we give that to the terminal, type enter, and it did absolutely nothing, which is good because that means it compiled. If we type ls, we now have this new program called simple that we can run, and this is where that dot actually comes in handy. To actually run a program that isn't a command, to run our compiled program, we say /. To run a program that lives in the current directory, we say /program. So here we'll do /simple. Okay? Dun dun dun. And that should be all we need to do. /simple. And hey, it does absolutely nothing. It makes no output. We just get another terminal prompt. And that's exactly the point because this program did nothing. But it worked. It was the simplest possible C++ program that we could have written. Okay, next slide. Complexity. We are going to deal with that a lot because all of our programs are going to be a bit more difficult to write in this class. It's a bit more difficult than CS8. So the idea is we're going to abstract away things. So really, when we write programs, they're going to be eventually translated into a form that runs on our CPU or our processor that's running with transistors and like passing electrical pulses all around, and those are our ones and zeros, right? But no, we think way up here with our software, with our high-level programming language, and eventually it all gets translated down through the compiler, through this thing called the assembler, into assembly code that represents, like, it's the last English-looking programming language before it gets to ones and zeros. This is machine code. And then we're going to eventually run our program on our actual hardware inside of our processor, using our memory, using our inputs and outputs devices, our keyboard, our mouse, our screen. And eventually this all goes down to circuits and actually runs on the bare metal using electrons. But we don't actually look at that as programmers. All we see are lines of code. Okay, so we abstract away any issues. For example, we, as programmers, love to abstract away hard problems. One thing that you already know how to do is write a bunch of functions. For example, you don't write a really long main function. Or in Python, you don't just write one really long line of code, one really long string of code. You'll split your file up into logical things that make sense to you, like functions. You'll write a bunch of functions instead to help you accomplish your task. Those are what is going to make it easier on your mind to actually solve this hard problem and break it down. Okay? Abstraction is key in this class. You want to break down all your problems into small bite-sized pieces. And another example is loops. Like, you're not going to write, you're not going to write print 1, print 2, print 3, all the way to print 10. No, you're going to write a loop that does that too, aren't you? Like, that's extra work for you. Why would you do that? Abstract away the process of writing a million lines that do the same thing. Write a loop instead. Okay, so you already know about complexity, and the key is abstracting it away, and we're doing that. Okay, so just to make sure that you're on the same page, that you've understood all of this, maybe pause this video and try to answer this, and then we'll come right back and answer it ourselves, or together. Okay? So the answer is, I could circle it and save this for posterity, what converts a high-level language into a machine language? That is the compiler itself. So the compiler takes your actual program and converts it into machine language. The operating system is like your Windows, your Mac OS. Your compiler is a program that is going to eventually, oops, I keep clicking that. Your compiler is a program that's eventually going to write another file that is your executable program, and you're going to call the print function inside of it, and maybe that print function will do some operating system specific things. But no, it's the compiler itself that actually translates a language, a high-level language like C++, into a machine language. Okay? And then Lab 0, I think we've talked about it. You're going to make a very simple hello world kind of C++ program. I'm essentially going to do it all right now for you anyway. But I do then want to talk about logging into a virtual machine, just in case you ever need to. I do encourage you to do what I talked about here in this lecture notes. I want you to get a terminal on your own computer. But in any case, just so that we're all on the same page, I want to make sure that you can also connect to our UCSB lab computers, and I'll give an example of that right here. Okay, and yeah, before I give that demo of remotely connecting to a computer, maybe we should just go to Lab 0 very quickly. Lab 0, you're going to write like a hello world function. All it needs to do is print out, hello world, I'm ready for CS16, and that is your lab for Monday. That is all you have to do. You get 100%. It counts as one of your labs. Okay? So that's what you're going to be doing. Now let me show you how to connect remotely to a computer. Okay? Connecting remotely to a UCSB lab machine via what's known as SSH. SSH, which stands for Secure Shell. Okay? So I do encourage you to get your own terminal. Terminal working though. So on a Mac, you can run SSH through the terminal. Or if you're in the Linux VirtualBox thing that I gave you, you also have the SSH command. Or on Windows, you can also use this program that you can download from the internet called Putty. I think that's how you say it. It might be it might look like that. But it'll give you the ability to connect to a virtual machine at UCSB. And all of those machines have names that are like websites. So it's always Cecil and a couple numbers. Oops, did not want to open that. It's always Cecil dash some numbers .cs.ucsb.edu. And those numbers go from like 00 to like 30, I think. And so let's practice connecting through SSH. So to connect, you need a College of Engineering account that I hope you have made already. My username is my first name and my last name, and I'll be using that. So for example, the command when you're using SSH is SSH Lawton Nichols, because that's my username, at the computer you want to connect to, Cecil dash, I don't know, 14.cs.ucsb.edu. Okay, that's the idea. And then that'll ask you for your password if you have that configured. But that's all you have to do. And then on Putty, your username is this. You don't actually type this command. But you'll give your username, you'll say you want to connect through SSH, and then you'll give the computer that you want to connect to. So let me copy that. Oops. So in that example, this is for the terminal command, is my username, and this is the computer I want to connect to. Your options are Cecil-01 through Cecil- I don't know. I think it gets into the 30s, 30 something. I'm not sure. You can try. Okay, so I'll connect to 14. SSH Lawton Nichols at cecil-14.cs.ucsb.edu. And then you say, yes, I want to trust this computer. I've already saved my password, and so it's just going to connect me into this computer. But otherwise, you'd be typing your password, and you hit enter. So this gives me a terminal on another machine. This is not my computer anymore. I have different files. If I do pwd, this is supposed to be my home folder. But no, it's different now. This is a different computer. I have different files. A lot of stuff from other classes, like old CS16s, CS8, grad classes. So this is a different computer's stuff, and I can compile things. I can say g++ astf.cpp. Like I can run things. I can get these files. There's a way to do that using something called sftp. But this is a different computer, and you might eventually need to use this. This is always available. If you can't get anything else working, you can connect through SSH. Then you can say exit to log out, and then you're back here. Okay? That is how you connect to a remote machine, but please try to get your own terminal working. Oops, that's a your. Because obviously something might happen. We're all remote right now. It's probably better to get your own terminal right now. And then yeah, let us write now a few more things. Let's write a program that says hello world, because that's the most default thing that we can do, that actually says something. And yeah, we'll go from there. I have a couple more files. This is a bit of a longer lecture, but I think that just means that the Wednesday lecture will be a lot shorter, right? So we know we need this in a program. And this is what it's going to look like if we want to print stuff. We'll include this library, and then we'll write our code right here. This is also important. Okay, so include iostream. Then cout, 2 arrows, hello world, 2 arrows, and then another string. So I can type a bunch of stuff. As long as it goes between these arrows, I'm sending it to this thing called cout that outputs things to the terminal. And I want to save this as hello.cpp. Okay, and so now I'll compile and run this by saying, remember, g++ hello.cpp-o, and then the name of the program that I want it to be called, so hello. So I'll compile this after I save it. And then I can run it with /hello. Oh, but I was doing something wrong. this compile, and then run /hello. But I was doing something wrong. This IOStream, this is a library that gives me cout, which you can think of like a function that prints things. But it lives in the standard library. It lives in the standard library. And so, and everything that lives in the standard library, which needs to be, which is all prefixed by this thing called std : all right? It is prefixed, or everything in the standard library is prefixed by std : So if I want to use cout, I have to say std : cout. And now it will actually compile. This is the first example of a compilation error, okay? It wasn't working for me, all right? So a compile time error or compilation error is one that the compiler gives back when it refuses to compile your program. So you won't even get to run this program if there's something wrong. And here it told me what was wrong on this line. It said line 6. Okay? What was cout? Okay, I told it what cout was. It's really this one that lives in the standard library. Now I'll save it and recompile. Every time you make changes, you have to recompile your program. And so now it's made it. I have this hello file, ./hello. And now it prints out hello world. Now, some things I can do is combine these, like this is all just one big string, right? I can say hello world like that, and then a synonym for this \n character is endl for end line. But again, that lives in the standard library, so I can say std : endl. And now, again, it'll do the same thing. Maybe I'll add an exclamation point this time. It gets pretty tedious to type this std : all the time. So there's a shortcut. A shortcut for std : all the time is using, the using keyword. So you can say using namespace std, and now you can get rid of these colons. Okay? Now I can compile, just say cout, just say endl, and run this program, and it works. So cout prints anything given to it by these little arrows, okay? And you can chain those just like I've been doing. But you can also just give it in one fell swoop. You can just say like that, for example. Not a problem. Okay, so that's that. That's our hello.cpp file. And now, let us go back here, and that happens to be the end of our slides. So I want to talk about a few other kinds of errors before we wrap this up. So let's see here. I want to talk about some types and then also about inputs. So let me make another file called types.cpp. I'm definitely going to be outputting things. So I'm going to include IOStream for cout. I'm going to say using namespace std. And I'm going to make my main function int main because it returns an integer. And it always returns 0 if things go right. Let me write a file that talks about the different kinds of types we have in our program. Okay? So the first thing, the first type we already know about is integers. So I can say int x equals 5. Okay? To declare a variable, I have to also give its type. All right? And now, you might also be wondering about these braces and these semicolons. So white space doesn't matter in C++. Instead, we use braces for blocks of code, like for functions, and semicolons to mark the end of lines. All right. So I say int x equals 5 semicolon because I'm done with that statement. I say return 0 semicolon because I'm done with that statement. And then main exists like this. So really, I could put all of these on the same line. Indentation doesn't matter. This should look very weird to you as a Python programmer, but C++ doesn't care as long as things are in between like this, or in between in these indented forms. Okay? So now I have an integer x. I can print that out. I can even say x equals x plus 1. Now x equals 6. I can see out x. And then a new line, let's say. If I compile and run this, again, G++, the name of the file, types.cpp-o, I'll call it types. It compiled. I now have a program called types./types to run it. Now I see 6. All right, so that's ints. Ints stand for integers. Now we also have bool for Booleans. B equals true or false. I can print this out, see out B. It actually gets converted implicitly. See out automatically does it to 0 or 1, depending on whether it's true or false, which is a bit weird, but you can always write a program or an if statement eventually once we learn that to fix that. And then we have, let's see here, we have strings. If I want to use strings, I have to include the string library. And this is for cout. And this is so I don't have to keep using std : all the time everywhere. I also have strings. String s equals hi, let's say, and I can output strings. All right, and then a new line. If I compile that, it'll print out hi. And let's see, there's also floating point numbers, so double D equals 3.14. Double stands for double precision floating point numbers. Floating point number. So that's the kind of program, the kind of type that will give you numbers with decimal places. There's also a float type, float f, that is like not as nice. It's single precision. It doesn't hold as many decimal places. So we tend to use doubles in this class instead. All right. Then we can output that, of course, cout d and l. And then one more, because I've been using strings with double quotes like this. There's a type of single characters, char c equals a single character. Single characters live in the char type. You have to use single characters to denote a char. And you have to use double quotes for strings. You have to use double quotes for strings. You can't use single quotes. That doesn't work, okay? Because it thinks you're trying to type just one character, and then you typed a bunch more. That wasn't wrong, or that wasn't correct in its point of view. Okay, so I can see out C and L. And now when I compile and run this entire program, and I can type the up arrow to get the previous command, I see all these things. 3.14, C, hi. These are all the different kinds of types that we have in C++. And just notice that every statement in C++ ends with a semicolon, and every variable, when I first talk about it, I have to declare it, and I have to give its type. So here, before you use a variable, you must declare it, which means to give its type. You can also say things like, all right, here's int x, I'm declaring it, and then I'll set it. So this makes x available to use. We know, the compiler knows that it's going to only store ints, and then I can set it down here. I don't have to say int ever again because the compiler knows. All right, so that's my program. That's types.cpp. And I think that's where I want to end. Oh, actually, let's do one more file called input.cpp. So I've showed you output. Let's also show you input. So I'll copy most of this. There's also something called cin. I don't need to use strings, I don't think. Let me output. Let me get an input. So let's say int x, and then ask the user to enter some number. Cin x. But first, cout, enter a number, please. And give it a colon. Don't have a new line so that the user starts typing right after this. Get the number from the user. And notice the arrows. So it's done for output because information is being given to cout. And then it's to the right for input because information is being taken from cin to give to x. Okay, so this will get a number. Then we can see out you printed, or you typed x, and then maybe an exclamation point and a new line. All right, so if I compile and run this program, my input.cpp file, I'm going to go like this, g++ input.cpp-o input. Enter a number, please. And now cin is taking over. It's saying, all right, type in a number, hit enter, and then I'll make this be your x. So I'll type 42, hit enter, and then it got saved into this x variable. And then it says you typed 42. Perfect. So that was a lot. That was a longer lecture than usual because we have a lot of things. One last thing, I think, just to make it slightly more fun, is I made this fancy karaoke program that breathes life into all these programs that we've been writing because they've been a bit boring. I'm going to put this video on YouTube, so I cannot actually include this song, but here's the idea. I've made this pause function that causes the program to wait for a little bit. So if I say pause 1, it waits for 1 second. If I say pause 3.14, it waits for a certain number of seconds. You don't have to worry about this. I had to look this up, so don't pay attention to this function because I'm never going to ask you to try and implement this. I just want to show you that you already know how to write cool programs in C++. So all you know how to do so far, we can call this pause function that I made for you. You can pretend it's from a library. And then we can print things to the screen. And so one thing we can do is play back songs. I can't play the song with you right now, unfortunately. I would be doing it in class because then copyrights aren't a problem. But now, because it's on YouTube, we do have a problem. But what this program does is if you click and run it, if you compile and run it, and then you start this song, as soon as it prints out starting now, then it'll play the song's lyrics to you in order, and the song happens to be Lizzo. So, if you want to find this song for yourself, Lizzo's Truth Hurts, compile and run this program. This will be the last thing that we do today. /karaoke. So go ahead and click play if you like right now, and then eventually once Lizzo starts singing, it'll actually follow along with the song, and it's pretty cool. So I think that this is where I will end this. I'll let this play for a little bit just so that you can see how it's working. It's pausing, it's calling this pause function to wait a little bit, and then it's printing out the lyrics of this song, which is really nice. It's super interesting, and it's everything that you already know how to do. So I think I'm going to stop us here. Thank you for putting up with me for this first lecture, and I will see you next time.